Hi everyone, in this video we're gonna introduce a special type of functions which is also used extensively everywhere, to be honest, and these are so-called continuous functions. And to start with, I want you to think about any function from the real numbers to the real numbers. Think about it. Draw maybe the graph of such a function. And I think you will draw something like this. And this is a perfectly valid function from the real numbers. But this is actually something very special because I could define something from R to R. And I could map x to, well, let's say 0 if x happens to be a rational number, and to 1 if x happens to be an irrational number. So if I would try to draw this, then it's not possible because I'm not switching. I cannot really draw this. Or you've also seen the floor function of x, which the graph of which was something like going up, going up. And so what I can see here is this is something like a fluent line. I can draw this in one go. Whereas here I see some holes in my graph, and here I can't even start drawing this thing. And actually in machine learning we will be very interested in these type of functions, and we call them actually continuous functions. And of course the word continuous actually refers to that this is a continuous line in a certain sense. But we have to be careful because there exists a rigorous definition, and I will give this definition because it actually reinforces our usage of mathematical symbols. Well, I say first of all that if a function, let's say from R to R, is continuous in a real number, if, and this is a famous, like what we call epsilon delta definition for every, and I'm going to write it out in all symbols, and then I'm going to draw something to explain the idea. If for every epsilon you take smaller than 0, well, there exists a delta which is bigger than 0, the epsilon is also bigger than 0, such that it holds that if x minus a, the absolute value, is smaller than delta, then the function values, the difference between the function's values in this x and a, absolute value is smaller than epsilon. Let's draw what this actually means, because I'm guessing that if this is the first time you see this, you have to think a lot about this. Let's say I make something continuous, draw something like this, and here is my a. So I know that f of a lies here. And now if I take any epsilon bigger than 0, I can actually look at fa plus epsilon and fa minus epsilon. So I can draw a strip which contains exactly in the middle the function value f of a. Well, then the definition says that I can draw actually a strip around a, x minus, not x, a minus delta and a plus delta, which says that if I'm in this strip, then my function value will also be in the green strip. So basically this says that you can do this for every epsilon. So the more narrow, so regardless of how narrow you draw this green strip, you will always be able to draw a blue strip around a, such that from the moment you're in the blue strip, the function value will be in the green strip. And think about it. I know it's not easy. By the way, this is something I specifically defined in R to R, from R functions from the real numbers to the real numbers. You can define what it means for a function to be continuous in any metric spaces x and y, whatever that means, just to say that we will actually gonna look at continuous functions from Rn to Rm, but it's not necessary to actually define it. Just think about continuous as something that is in a continuous line, but to make that expression clear, actually I need to say that f is continuous as a function if f is continuous in A for all A in R. So if you have a function for which this property holds for every A of my domain of the real numbers, then we say that it's continuous, and then this graph will indeed be something like a straight line. There's another way of saying this, using a different concept, if and only if we take the limit of x approaching A, then this is exactly the function f evaluated in A. I'm not going to explain what it means to be a limit. Again, you have a rigorous definition using a similar epsilon delta definition. The reason I put this limit concept here is we're going to need it in the next movie as well. One small example to end. I can draw the following function. So what you can see, this is definitely not a smooth line, a continuous line, but this function f is continuous in the point 0. So just to say that there is really a difference of being continuous in a certain point and the function f on its own, in the whole function being continuous. If it's continuous for every point, then indeed the graph will be like a continuous line. Anyway, in the next video we're gonna look at even more special functions, and I promise you that's the last thing we're gonna need. Ciao.